Okay, so foundation models. They're learning to see without needing human labels. And wow, the results. They're pretty stunning. We're digging into DINOv3 today, this new universal vision encoder that really shows massive scaling can work if you figure out how to fix things along the way. Welcome back to Artificial Intelligence, Papers and Concepts. I'm Jack Malik.
And I'm Sophia Lane.
And yes, if our voices sound maybe a little too consistent, it's because we are indeed AI-generated voices.
That's right. We're here to present the concepts curated by Dr. Sadi Malik. Our mission today really is to give you a solid shortcut to understanding the DINOv3 foundation model. This comes straight from Meta AI research. And DINOv3, it's not just another update. It feels like a pretty big shift in using self-supervised learning, SSL.
All right, the core idea seems so powerful. Get rid of the need for manual data labeling, just completely.
Right.
Which then lets you scale up effortlessly to these, well, enormous and varied data sets. We're talking everything from normal photos to like specialized aerial shots.
All with one single algorithm. That's the goal. And to pull this off, the Meta team focused on, well, basically two big things. First, just extreme scaling. Data, model size, everything bigger. But that brought problems, instability. So the second part was fixing that instability. They came up with this really clever repair technique called gram anchoring. It deals with the feature degradation you get from training for so long.
Degradation. Okay, we'll definitely need to unpack that.
For sure. And the payoff is this super versatile foundation model. You can take its frozen backbone, no fine-tuning, and it often meets or even beats models specifically trained for one task.
Impressive. Before we dive deeper, though, this podcast is sponsored by BigVision.ai. That's a consulting and product development company helping businesses of all sizes with computer vision and AI solutions. You can reach them at contact@bigvision.ai. And so let's tackle that scaling challenge first. We know SSL, like we saw with DINOv3, it's great because there's almost unlimited raw visual data out there. But DINOv3 already had a 1.1 billion parameter model. What happens when you try to go even bigger? Where do things, break?
Yeah, the paper points out a few key issues. I'd say they boil down to maybe three main things. First, just handling the data. You've got, say, 17 billion unlabeled web images. How do you even know what's useful in there? It's messy.
Right, just a massive pile of images.
Exactly. Second, there's optimization instability. Traditional training schedules, like cosine decay, they kind of need you to know upfront exactly how long you're going to train for, the optimization horizon. But with these huge, maybe constantly growing data sets, that's just impossible to know beforehand.
Okay, data curation and training schedules. And the third one sounds odd. Performance degradation, you train longer, it gets worse.
It's counterintuitive, isn't it? But yeah, the research showed that for models bigger than VT large, that's about 300 million parameters, the actual quality of the features can start to drop after a certain point in training.
Huh. So more isn't always better, at least not straightforwardly.
That's the paradox they ran into. And DINOv3's approach to scaling was, well, bold. They pushed the architecture way up to a custom VT7B model. That's 6.7 billion parameters.
Whoa, 6.7 billion. DINOv3's largest was 1.1 billion, right? So that's almost 7 times bigger.
Around 8 times, actually, than their previous largest. It's a massive leap.
Okay, jumping from 1 billion to nearly 7 billion parameters. You must need to be incredibly careful about what you feed it. How did they handle the data quality and stability for such a monster model?
Meticulously is the word. They started with that huge 17 billion image pool. But then they used clustering techniques. They created this curated subset, LVD1689M. The clustering was key for balancing the types of visual concepts and also for filtering out junk, basically.
So not just throwing everything at it, but smart selection.
Right. And they mix this balanced web data with images found using retrieval. So finding images relevant to certain concepts. Plus, they threw in standard data sets like ImageNet 1K for good measure, high-quality benchmarks.
Got it. And the optimization horizon problem, the issue of not knowing the training duration.
They just ditched the traditional schedules completely. They trained for a fixed number of iterations, 1 million, but used constant schedules. Constant learning rate, constant weight decay, constant momentum for the teacher EMA.
Constant, so no decay.
Nope. This means they didn't have to guess the total training length. They could just run it, see when performance leveled off, or, crucially, started to degrade. Much more flexible for massive scale.
Okay, which brings us right back to that feature degradation problem.
Yeah.
If constant schedules let you train longer, what happens when you do train too long, especially with these giant models?
Right. This is where the feature collapse idea comes in, but it's specifically about the local patch level features. Think about it like this. The model gets really good at understanding the big picture. Like, okay, this is an image of a cat. Global understanding improves. But while it's focusing on the catness, it maybe starts to lose track of the exact texture of the fur in one specific patch, or the precise edge of the cat's ear.
Ah, so the overall classification gets better, the main CLS token works well, but the information in the individual patches of the image gets mushier, less distinct. The paper mentioned cosine similarity increasing.
Exactly. The patch features start looking too similar to each other and too similar to the overall summary token. Feature locality just fades. If you look at visualizations, the patch similarity maps get noisier, less defined as training goes on. And this directly hurts performance on tasks that need that local detail, like semantic segmentation, knowing exactly which pixel is cat and which is background. Their results showed MIOU, the segmentation metric, dropping off significantly after maybe 200,000 iterations for the big models.
That's a major roadblock then. You scale up, solve the training schedule issue, but the core visual understanding where things are starts to break down. So how does DINOv3 fix this? This is the gram anchoring part, right?
Yes, gram anchoring. It's basically like a late-stage repair job. They apply it only after that initial long training run, after the 1 million iterations.
Mm.
The goal is to nudge the local feature relationships back into shape, but without messing up the good global features the model learned. And it works using the gram matrix.
Okay, gram matrix, quick refresher for those of us whose linear algebra is a bit rusty.
Yeah.
What is that here?
Fair enough. Think of it like a map of relationships between all the little image patches. You take the feature vectors for every patch in an image, and you calculate the dot product, basically, the similarity between every single pair of patches, that whole matrix of similarities. That's the gram matrix. It captures the structure of how all the local features relate to each other.
Okay, structure of similarities. So DINOv3 uses this gram anchoring to make sure the structure in the current model, the student, stays close to the structure of a gram teacher. But who's the teacher? Why would its structure be better if the student has degraded?
This is the clever bit. The gram teacher isn't some external model. It's just an earlier version of the same model being trained.
Wait, really? You use an earlier checkpoint?
Exactly. Because those earlier checkpoints, from before the feature collapse really kicked in, they still had better local detail. They remembered where things were, even if they weren't quite as good globally yet.
So you're essentially using the model's younger self, the one that paid more attention to details, to guide the older, more generalized self to keep its local structure intact.
That sounds neat. Does it matter which early checkpoint you use?
Seems like the method is pretty robust.
Eh?
They add a specific loss term that pushes the student's gram matrix to be similar to the teacher's gram matrix. It basically anchors the student to that earlier, more structured spatial representation. And they found an enhancement that works really well using higher resolution features for that gram teacher.
Higher resolution, you mean feeding the teacher images at like double the pixels?
Precisely. Run the gram teacher on higher res input, get those features, maybe downsample them a bit, and use that richer structure as the target for the student. It distills even finer grained patch consistency into the student. And it gave them a real performance bump, like an extra 2 MIOU points on the 80/20K segmentation benchmark, just from this trick. That is clever. Distilling just the structural information from a higher res view. Okay, so scaling, constant schedules, and then this gram anchoring repair. What does this all add up to in terms of actual performance? The proof is in the pudding, right?
Absolutely. And the results are really where DINOv3 shines, especially on those dense tasks that need local understanding.
Yeah, the paper's qualitative results, like the PCA maps of features, they describe them as much sharper, less noisy, more semantically coherent than strong models like DINOv2 or even siglib2.
And the numbers back that up. Quantitatively, even just using the frozen backbone, no fine-tuning, just adding a simple linear layer on top of the performance is exceptional. Semantic segmentation on 80E20K, state-of-the-art 55.9 MIU. Remember, MIOU measures how accurate the pixel masks are. Beating specialized models by nearly 3 points with a frozen backbone is, well, it shows how good the base features are.
And it wasn't just segmentation, right? Depth estimation, too.
Yep. New state-of-the-art for monocular depth estimation. Needs really precise spatial understanding. Lowest RMSE, that's root mean square error, so lower is better on like standard benchmarks like NYUV2 and Kitty, more accurate depth maps.
Okay, so dense tasks are clearly a win. What about robustness and maybe more global tasks?
Still very strong. It got the best score on ImageNet-C, which tests robustness against corruptions, 19.6 millisE, which is top tier. And it also did extremely well on non-parametric tasks, things like video segmentation tracking, where temporal consistency matters, state-of-the-art there too, and unsupervised object discovery.
What strikes me is the implication for building complex systems. It sounds like DINOv3 isn't just a good standalone encoder. It could be a foundational piece you build upon without constantly retraining the core.
That's exactly the potential game changer here. You take a complex pipeline, say for object detection or segmentation, you swap out the usual backbone, plug in a frozen DINOv3, and performance often just jumps up. The paper shows this clearly. Plain DTR, an object detector trained on frozen DINOv3, state-of-the-art 66.1 MAP on COCO, mass2former for segmentation, put it on frozen DINOv3, equals state-of-the-art on 8020K at 63.0 MIOU. And crucially, you need to train far fewer parameters downstream. Makes things way more efficient.
So it's like having this incredibly solid, universal visual understanding engine that you can just rely on. Did they test this universality idea? Like, does it work on data that isn't typical photos from the web?
They did. They took the exact same SSL recipe, the scaling, the constant schedules, the gram anchoring, and applied it to geospatial data, satellite images. They pre-trained a model on a dataset called SAT493M. The results were great. The DINOv3 satellite models got state-of-the-art in things like estimating tree canopy height, significantly reducing the error, and they set new records on 12 out of 15 tasks in the benchmark suite. Really shows the approach is domain agnostic.
Okay, that's compelling universality.
Yeah.
But that 7 billion parameter model, it must be computationally intense, right? How do regular users or companies get access to this power without needing a supercomputer?
Good question. Knowledge distillation is the answer. They took that huge, powerful 7B teacher model and essentially transferred its knowledge into a whole family of smaller, much more practical student models. They released VIT small, base, large, and even a VITH plus back.
And how well did that distillation work? Do the smaller models retain the magic?
Remarkably well. The VITH plus model, for instance, is 840 million parameters. Still big, but, 8 times smaller than the 7B teacher. Yet its performance is pretty much on par with the giant teacher model across many tasks. It validates the whole approach. You can capture the benefits of extreme scale and gram anchoring in more manageable models. And they didn't stop at VITs. They even distilled the knowledge into completely different architectures, ComNexts. And these distilled ComNext models actually outperform the versions that were trained supervised from scratch, especially on tasks involving out-of-distribution data or higher resolutions, shows the flexibility of the learned features.
So DINOv3 really feels like maybe a turning point. We're looking at an era where maybe you don't need to fine-tune a massive backbone for every single specific visual task. You could have this single, universally trained, frozen encoder that just works, meeting or beating specialized models. It's that combination, the huge scale, the clever constant scheduling, and that essential gram anchoring repair that unlock these really versatile, robust visual features. If hearing about this has got you thinking about diving into computer vision and AI yourself, or maybe leveling up your skills, we really encourage you to check out opencv.org/university. They've got courses for all levels. That's opencv.org/university.
Well, thank you for sticking with us through this deep dive into the DINOv3 technical report. We hope this breakdown gives you, the key insights into what makes this new generation of visual foundation models tick and maybe how you can leverage them.
Absolutely. Join us next time as we continue exploring the frontiers of AI research. Until then, make sure you're subscribed and keep learning.